maybe we start now, or we wait for another 1-2 seconds.
Okay,
We could
I'll
wait for 5 seconds. Okay. Okay, maybe we could get started now.
Yeah.
Yeah.
Okay.
Yeah. Maybe.
Yeah.
Oh,
Yeah, you could introduce the speaker.
Okay. So today we're very glad to have Yuchen Zhu to give us the talk beyond Euclidean data for diffusion models. Yuchen is a third-year PhD in machine learning from Georgia Tech, supervised by Molay and Yuchen. His research centers around developing diffusion models for non-Euclidean data, especially those discrete and multimodal data. Yeah, thank you for coming.
All right. Thank you, Jiajun, for introducing me. I'm glad to have the opportunity to share with you guys two of the recent work from our group on building diffusion models for non-Euclidean data. And today I'll be focusing on two cases. One is Lie group. The one is on Lie group, and the other is for multimodal data. All right. So sure, everybody's already familiar with the amazing things Euclidean diffusion model can do. It can do a lot of things we really well now. For example, you can turn your own photorealistic images into cute cartoonist Ghibli scale images. On the left is a self-portrait of me and my lovely cats, and they're now turned to wonderful art creations. But also, they can also do things like screen test rendering, which used to be extremely difficult to do so, for generating text that is clear and without blurry in images. But these are all advances of a diffusion model in Euclidean data, but there are actually much more other modalities beyond the purely Euclidean ones. And they're all to me, they're all of equal importance. For example, there's manifold data, such as those usually shows up in robotics or protein applications. There are large corpus of discrete categorical data, such as DNA sequences or tags or protein sequences. And more importantly, there are also the real applications. There's like is a full abundance of multimodal data, which contains a mixture of all these modalities discussed before. So how do you do diffusion general models on these data modalities is a separate question that worth our investigation. In the first part of the talk, I'll be talking about how to build diffusion models for a specific type of manifold called Lie groups. In the second part of the talk, I'll be talking about how we approach this general modeling of multimodal data using diffusion models. Yeah, so in part one of the talk, I'll be talking about this work on triple-X diffusion model for Lie group generation. Lie group data generation is a joint work with Tianrong Chen, Lin Kaikong, Evangelos Theodoro, and my advisor Molay Tao. And the work is published in Clear 2025. Right. So I'm sure everybody here is very familiar with what is diffusion model for Euclidean data. The most important is that it contains these two process, this forward and then backward process, where the one above add noise to your process that turns your any data distribution at time zero into prior distribution, typically standard Gaussian at time one. And it's time reversal, which is the backward generated process, reverse this process and start from the prior and leads to new data generation as if it's sampled from the data distribution. But of course, this process cannot come in for free. To do generation, you will require learning something extra. That is, usually this is the score function, as I circled here. And this is typically done through optimizing this Spinozzian score matching loss. So let's say now we want to build a diffusion model for manifold data. By doing this, we mean that data distribution is supported actually on non-manifold M. Note that this is in contrast to the popular hypothesis, the data manifold hypothesis, where it says that approximate data lies on some low-dimensional manifold. Here, we're working with the cases that we do have explicitly known manifold, and our data lies on that. And this manifold is typically closed, known to as have a closed form expression. This brings some new challenges compared with the Euclidean case we've seen before. essentially you have the questions on every component of the algorithm design. For example, for the forward dynamics, we cannot easily adapt that OU process to the manifold cases, as this typically will renders the drift to be undefinable for a manifold. Some choices will say that some existing solutions will say that let's get rid of the drift and only add noise, which corresponds to the sparse exploding schemes. But it also gives the question that we need to exactly simulate the manifold Brownian motion in order to be able to simulate this forward dynamic, which could be challenging. The issue right with the forward dynamic is this choice of prior distribution, which typically is the stationary distribution of the forward dynamic you choose. Now, to do general modeling on manifold, you would need to have some simple distribution that is easily sampled from on the manifold, and this could also be hard to get. Of course, on manifold, we have to rethink our choice for score function and how do you learn that. And there are already a lot of amazing works targeted at addressing this problem, such as they typically aims at general manifolds, and these works, such as the Moser flow, Riemannian diffusion model, Riemannian score-based general models, Riemannian flow matching, and many more, has bring great advances to the field, and a lot of them are best paper or runner-up or best papers. So what we want to say is that this problem is although there's all these excellent work and amazing solutions to the problem, we can still do better if we're focused on a specific type of manifold and we leverage the structure there. So today we're going to so for this part of the talk, we'll be focusing on Lie group, which is a special type of manifold, has additional group structure, and we'll be seeing how we can leverage this additional structure that usual general manifold does not have, and to make a better general modeling algorithm. Right. So our yeah. So before we get into that, we can first want to know what is Lie group, right? So in short, Lie group is simultaneously some sort of smooth manifold and also has a group structure. So took, for example, the special orthogonal group of order n, which we use it to characterize all sorts of rotations. It is abundant in applications like robotics or structural biology, in all these physical and biological applications. So it's highly relevant to the description of angles. Right. So SON can be described as this set of n by n matrices, which are both orthogonal and has a determinant one. So we can have two different perception of this object SON. First, you can think of it as a group, right? So for two different type of rotation, two elements G1, G2 in SON, we can define a group action between them, so that the result will still be a group element. For example, if you have two rotations, the combination of them will be sequentially applied to rotations again. And then, of course, this will be some sort of rotations, which itself is an element, this SON group. But other than that, we can also perceive it as some sort of a manifold. So for an element R that belongs to SON, we can in fact define the tangent space, this geometric object of this manifold at this position R, which again is a set of n by n matrices satisfying different constraints. Right. So these two structures combined leads to interesting results. That is, we can decompose the tangent space of this Lie group at position R into a result of two simple expressions combined together. So essentially, the tangent space, which is the geometry dependent component, can be written as the position R left multiplied by any an element in the Lie algebra SON. This Lie algebra essentially is the tangent space of this Lie group at the identity element, and it's in this case it consists of this simple set description. So essentially, it's a set of skew symmetric matrices. And important thing is that this is essentially isomorphic to some Euclidean spaces, because for skew symmetric matrices, you just need to, or you can choose freely what is the element in off diagonal, above the diagonal, and you get the rest of the entries directly. So this is essentially some flat Euclidean space. So this group structure plus manifold structure give us a very nice decomposition of the complicated tangent space, which depends on, of course, the geometry of the manifold. One simple way of understanding this relationship is to look at the cases where n equals to 2. So in this case, this SO2 is essentially the unit circle, and the green line is a line, it's the linear space, it's the tangent space of the manifold at the identity element that is isomorphic to R. And the red line will be this the tangent space of the manifold at this rotation angle R. As you can see, you can think of this red line as this green line, this linear space rotated by the angle R to this position. So explaining what we're seeing here. Right. So this is the spectral structure of Lie groups that usually a general manifold does not have. How do we leverage this to actually build a better diffusion models tailored to this manifold and its distribution on it? The idea will be to leveraging this idea called left trivialization, and plus we want to use momentum dynamics. So what we mean by this is to consider this type of dynamics as our forward dynamics. So here, GT is essentially our state variable that belongs to the general Lie group G. So the GT causality is what we call the trivialized momentum that stays the Lie algebra in this small g. And in general, if we're running some dynamics on manifold, the velocity of the state variable will have to stay in the tangent space at this position. That's where our GT causality represents. This is the usual momentum. The reason we can express the velocity in this way is because we exactly leverage the decomposition we said before, that the tangent space can be written decomposing to some element, your current position, and some element in the Lie algebra. And for the Kasai dynamics, we're just adding usual, because it's Euclidean, we're just adding usual Gaussian noise to it, following a simple OU process. While this dynamics might seem simple, but it does actually amazing things. This is, I want to emphasize that this is not exactly an analogy of the usual kinetic Langevin dynamics on Euclidean, because here we actually consider a nonlinear drift for G. This decomposition GT of the velocity in the phase space as the product of GT causality actually introduce nonlinearness into the dynamics. So even if we just add simple Gaussian noise to the Kasai dynamics, we'll be able to do special things. So this dynamics is provably converged to a simple prior distribution. So if you start this position GT from the data distribution, and the momentum you initialize this then with the Stern Gaussian, and at large time t, they will probably converge fast to this hard measure on the Lie group, and the momentum will remain invariant being the standard Gaussian. So this hard measure essentially is a generalized notion of a uniform distribution if we work with compact Lie group. So therefore, it's easily sampleable if you're using some tricks from random linear algebra, and this is a known results. What's amazing about this dynamics is also that we're actually only injecting noise through the Euclidean variable through this simple OU process. And this has actually a lot of amazing benefits. So one of the amazing benefits is that if we use this as the forward process, as we said before, if we derive it's a backward process, backward generated process that takes the start from the hard measure across the standard Gaussian and map it back to the data distribution across the standard normal. We'll see that the extra term, only extra term that pops out is only showing up in the dynamics for Kasai. And since Kasai, just like what we've seen usually when we reverting Euclidean diffusion models. And more importantly, because this Kasai is a Euclidean variable, now the score actually the score we want is actually only the gradient of this log joint distribution with respect to the psi. So therefore, this itself is a Euclidean gradient, and there's nothing dependent on G in this expression. So everything seems to reduce to the case that we usually work with as if the things are Euclidean. This, of course, has a lot of key benefits. Having the ground truth score to be Euclidean enables very flexible neural network design, as you don't have to design neural network to tailor that so that it fits the output of the tangent space at this manifold, which is position dependent and geometric dependent. So this gives us a low approximation and learning error. And more importantly, this has additional structure that this momentum structure enables us to use advanced integration techniques such as exponential integrator or split integration for low simulation error and zero projection error. So what we mean by this integration techniques is that if we look at this generated process, the dynamics itself is highly nonlinear. The drift for G is a nonlinear combination of G and psi, and the drift for psi also has a nonlinear score function here, which is hard to deal with. But in fact, we can do this operator splitting and turn this into the sum of two much simpler dynamics. So for the first dynamics, we're actually just fixing the momentum and moving, trying to move constantly on the manifold with a fixed velocity. For the second part, we're fixing the position G, and we're only evoluting the momentum psi, which is running the simple OU process with a constant nonlinear drift, of course. And we can apply exponential integrator for both of them. On the left, this means that we're just moving geodesically on the manifold, following using this the exponential map of the Lie group. On the right, we can adopt exponential integrator that exactly integrate these linear components of this linear drift and this Brownian motion, while additionally give additional treatment of the constant nonlinear term S. And these integration has a low approximate error, and additional benefits that this integration scheme is manifold preserving, which means that for whatever T you're having, as long as you're forming this numerical simulation scheme, we always have that the GT is element of the Lie group and the psi is an element of the Lie algebra. So we're never worried about stepping out of the manifold, and it has to, we have to post-process it to make it a comeback. Which is a typical case if you use the standard integration schemes like Euler scheme. So all these are very desirable. So powered by these designs, we can look at some of the application and good results we have. One important application is to generate protein and RNA configurations. So here I'm showing that we're generating torsion angles. The blue ones are the generated the data samples, and orange ones are the true samples. You barely see the orange ones because the overlap is there's a high overlap. So this means we actually learn the distribution very accurately. And this can also be seen from the fact that if we evaluate the test negative log likelihood on data sets, our method achieved very decent results, which outperformed these previous methods by a lot. Right. So apart from this biological applications, our method also can have good applications in quantum data. So here the data we're showing is some elements of high dimensional unitary group, which corresponds to the time evolution operator of different random quantum systems. And above is some quantum system called quantum oscillator. Below is the one for this transverse field EC model, which has a lot of applications in condensed matter theory and statistical physics. So again, our method captured accurately the ground truth distribution despite the complicated patterns. And for the fact that we are actually the first work to be able to generate the data on the unitary group. Finally, I also want to talk about the applications of application extension of TDM on material science. So this is not what we originally done in our work, but after we published this paper, a group of Denmark researcher from Denmark, expand our method to include additional modality and applied it to the task of crystal structure prediction. So their method names KDLM. It's a flexible extension of TDM, and as you can see from the table, it shows very near total performance on all these metrics on material science. These suggest again that our method works really well with Lie group data, and it's very effective and easily expandable. Right. So that's the finished discussion of on the Lie group, and now we'll be moving on to a more general setup where we're trying to build a diffusion model for multimodal data consists of more than one modality. So this method called diffuse everything is a joint work with Kevin Rojas, Yuchen Zhu, Felix Ye, and again my supervisor Mo Lai Tao, and it's published at ICML 2025. Right. So I guess I don't need to convince people that the joint generation of multimodal data is very important. While there are a lot of solutions right now already, existing methods usually has a very complicated pipeline. Yeah. So let's say we have a lot of different kind of data modalities, consider images, tags, or motions, or whatever. And existing methods, a large chunk of the existing methods typically approach this question with unimodal diffusion model. So what I mean by unimodal diffusion model is that you train the diffusion model is defined on a state space of a single modality. So in order to do so, in order to be able to adapt this algorithm to this multimodal data, the approach people take is to train some representation harmonizer, such as VAE, or tokenizer, such as Euclidean, so that either all the data are turned into continuous latents or discrete latents. And then on this state space of unified modality, people do build generated modeling algorithms and to generate new latents, and they try to decode this latents back to the original modality to finish the generation task. But of course, this pipeline is complicated and has a lot of dangerous design. The first one is that this representation unification is very challenging and expensive. It is known in the literature that training good VAE or tokenizer is hard and requires tons of engineering techniques. And moreover, this is usually only applicable in the applications where the data is abundant, right? If it says for like text and images, we have web scale data, and this is typically fine. But however, for other modalities where, such as a lot of in science applications, data are scarce. So the training of good VAE tokenizer itself is an extremely challenging task. Another caveat is that the generation performance is actually capped by how good you can decode these latents. Imagine that you learn a perfect diffusion model that generates very good latents distributions, but you have a very underperforming decoder, and that makes all your generated modeling efforts goes in vain, because there's no way you can get a decent result from this bad decoder. So what we've been thinking is that, why don't we just bypass all this, right? So we just start directly from the data, and we're trying to train some diffusion models that works natively for each data on their native state space. And by doing so, if we learn this model, we can do direct sampling of it to get the original modality, which bypass the need of VAE and this decoder. Of course, this one has a lot of benefits. For example, this one has a lot less modules. Will be much more efficient because we no longer need to use VAE in this inference or training problem. This also brings a new space for generative modeling of multimodal data, which are worth which worth more investigation. So yeah, so there are actually a lot of type of So for example, the examples we're most familiar with probably is text image. So here I'm showing the image of my lovely cat Lava. And to describe this image as a caption, a good caption of it will be, say, Lava with a pearl earring. Of course, this is a analogy to the famous painting Girl in a Pearl Earring by Johannes Vermeer. But what the message I want to say is that for this text image modality, the information conveyed by a message and by the text and by the images have correlation. They have to be consistent with each other. This is also the case in protein science, where of course you have a sequence and its folded structure, and the sequence of the structure are highly connected to each other. There's other multimodal data includes say tabular data, which also is of more and more importance. This mixed type tabular data suggests that our data means that our data does not contain only one type of things, like only numerical value, but also have categorical values such as their gender. So treating this will be something. Treating mixed type tabular data is something people do a lot in real life. And finally, there's also robotics applications where the modality you work with is some natural language instructions with the instruction you want, the motion you want the robotics to generate it, which is typically characterized in using manifolds. I want to say that there are actually already a lot of good solutions for each of the problem. For example, for this text image, there's some non-native space solutions, which means that it does requires representing the both text and images on the unified latent space, either continuous for as say for unit diffuser or versatile diffusion, or discrete for unity 3. Similar things happens for tabular data and for this robotics data as well. On protein structure, I want to emphasize that there indeed is a native state solutions proposed by this elegant work of multi-flow and generator matching, and etc., where they target directly at the protein sequence and trying to generate the protein structure together with generating a sequence. But I want to what we are trying to provide here is not some solutions that tailor to specific data modality. We want to provide a general native space solution that potentially could be extended to any combinations listed here. But of course, for the sake of presentation, we'll be focusing these two applications, which is also haven't been done in the literature. That is to co-generating text and images natively, and co-generating mixed type tabular data natively as well. Yeah. So how we can do with how can we do this with a diffusion model? So we're going to leverage the fact that a diffusion model are actually very versatile data generators, and this idea expand way beyond only Euclidean diffusion model. So, from my opinion, any generative modeling algorithms could be called diffusion model if they have the following, if they satisfy the following several properties. So, for the most important, of course, we will need to have a pair of dynamics where there's a forward noising process that destroys the information, turns any data distribution into a good prior distribution. And we need to find a backward process that reverts what we described before and start from the prior and generate new data from the data distribution. And to be algorithmically capable, we need this prior distribution to be simple so that when we run the algorithm, we can efficiently start from it, right? So which means that we want to be able to cheaply sample from this prior distribution. And of course, again, this backward generation, cannot just come to us for free. And in this process of learning this model, we need to learn some extra information about the distribution of the forward process. Typically, we call them the score functions in order to complete this generation. So I guess this will not surprise anyone that for Euclidean spaces, the narrow sense of diffusion model or the Euclidean diffusion model perfectly satisfy our definition here. We have seen this pair of time rescaled OU process and its backward process. And the prior we typically is work with is normal, is very is very efficient to sample from, and we can learn from this. We can learn it from using this score matching, the Gaussian score matching objective. But the idea indeed generalizes beyond that, right? So let's say we have another type of state space, like say for languages or for DNA sequences, we're going to work with a state space that is finite, that is a discrete state space. On discrete state space, we can no longer define SDEs because there's no continuous structure on there. Therefore, we need to pick a different type of stochastic processes as our forward process. And a good choice will be this continuous time Markov chain with transition rate Qt. So what I mean by XT distributed CTMC Qt is that this XT follows a jump process given by this transition rate Qt, and its evolution, its continuity equation is going to be described by this simple ODE. Right. So the trajectory of this XT will be just depending on how your Qt changes, it will be staying at state space each state space for random time. Then we'll make a jump and stay there again for random time. So that's what I mean by a jump process. Fortunately, for this thing, we can also derive its backward process, which again is a different continuous time Markov chain, just with a modified transition rate. We can in fact compute that in order for this to be the time reversal of the forward process, this transition rate just need to satisfy the simple equations, where it says that your modified transition rate can be computed using the ratio of the distribution of the forward process between two different states and the transition rate of the forward process as well. So this is what we call, again, this is aligned with what we said doing backward generation requires learning distribution info, and distribution info in discrete state space comes in the form of this distribution ratio. And we should call it a concrete score or a discrete score. And this, in fact, mimicking the role of gradient log probability in the continuous state space. And if we choose Qt, properly, we can make this the stationary distribution. We can make this process start from any data distribution, turning to a simple distribution such as uniform distribution or delta distribution at the additionally introduced absorbing mask token, depending on what of the Qt we choose. And we can also perform score learning, but this time it's not with using the L2 norm. It's going to be some term called Gaussian score entropy, which is grand truth is the true score we target here. So of course I'm listing only two examples here, but of course the TDM we shown before will satisfy this, and the Romanian diffusion model will satisfy this, and there are many more. Right. So we'll be thinking, how about we just use instead of just turning all sorts of data onto unified state latent space, why don't we just use a different type of diffusion model to deal with its original data modality we want? So we made this is that for images, we know it's continuous, so we want to use SDE to as the dynamics for this continuous component. For this text description, we know it's discrete, so we want to use a jump process, a continuous time Markov chain, a discrete diffusion to deal with it. But ideally, if we simulate this process, we should get this for a long time. We should be able to get an image with a pure Gaussian noise. This belongs to the prior distribution, and also a sequence of pure mask token. Also is the come from the prior distribution of the discrete component. Since we're stacking continuous diffusion with discrete diffusion, we call this continuous hyphen discrete diffusion model, just to highlight its algorithm component. So we want to learn this new type of diffusion model. But so there are of course there are several important questions we want to address. We start with these three most important. That is, what are the score function you need to learn in order to perform generation, and what does this backward process look like, and in fact how to learn these score functions. Right, these are the tricky questions that we need to address in order to work natively with using multimodal diffusion model for the modality of a mixture of different modalities. The answer is to look at this theoretical framework called denoising Markov models. So denoising Markov models, the work framework introduced in Joel Benton et al. In 2024. And essentially, in a high level, the work suggests that instead of looking at the different diffusion model at different state space, such as SDEs for Euclidean data, jump process for discrete diffusion on finite state space, or manifold SDEs for manifold diffusions for Riemannian diffusions, we can just use a very abstract notion, a very general notion of a Markov process with different generator to characterize that. So we can consider all this diffusion model to be a special case of this, where we are just switching different generator. For the backward process, it's also some Markov process with a different generator k theta. So to make this idea more concrete, we can look at some examples of this infinitesimal generator. This infinitesimal generator almost characterize exactly the evolution of all the property of this different kind of stochastic dynamics. So for the simple OU process on RD, its infinitesimal generator will be of the sum of these two differential operator. For the infinitesimal generator for this jump process, the generator will just be matrices, this Q transpose. Yeah. So for learning the backward process, similar to all we've seen before, we need to learn some distribution info, right? These things cannot come into at no cost. So that's why there's a superscript with theta, which essentially says that the k theta is implicitly parameterized with some distribution beta theta that you want to learn. And if you learn this is what we mean by this distribution info. And if we learn this perfectly, ideally this beta theta is approximately the same as PT, the Grunschus, the distribution of the Grunschus marginal of the forward process. Then at this moment, the backward generator process will be a good time reversal of the forward one, therefore performing the generative task we want it to be. All right. So how do we learn this? In Joel Benton et al. In Benton et al., they derive this explicit score matching objective for this general notion of Markov process. If you look at this, you see that this objective contains it pretty much only depends on the marginal of the forward process, which is given by depends on how you choose this for the Markov process with generator L. And in objective itself, it also depend only on this generator L. So of course, as all the explicit score matching object might suggest, this is not trackable for real applications because it contains this Grunschus distribution PT. Right. So but this is I'm presenting these results just to suggest just to show that this results actually this loss actually gives us the ideal optimal ones we want, because this loss has a minimum value 0 only when this beta theta is proportional to PT or equal to PT, let's say. So indeed, if we optimize this loss to to its optimum, we indeed can recover the ground truth information we want, so that we will be able to learn this backward process. Similarly, Joe Benden, just like the noise deriving different variants of trackable variants of score matching objective on RD, we can derive them in a general fashion into two different variants, which can be applied in different cases, depends on our scenario. The first one is what we call the implicit score matching, whereas we get it by doing some sort of integration by parts with the original explicit score matching objective. So in this objective, we no longer need any expression for PT. In order to be training with this objective, we only need to be able to evaluate its expectation with respect to PT. So this is typically can be done by just numerical simulation of this forward process, even if we don't have access to what PT really look like. Another more favorable choice would be to work with this denoising score matching variant, which additionally requires the conditional transition kernel of this PT. So while PT itself is hard to get, the conditional transition kernel is often given to us, or we can easily derive it. Just like in the Euclidean cases, this will be some Gaussian transition kernel with a time-dependent invariance and mean. Of course, we'll not be surprised that when we plug in this general notion of L into specific cases we've seen here, let's say the differential for the one that corresponds to the OU process, these laws exactly recovers to the form we're most familiar with. But now it's written in the form of beta theta. So it's written in the distribution form. But across all these losses, we can see that the term we can in fact does not really need to parameterize beta theta, but just need to parameterize its gradient log, which is what we call their score function, right? So does this suggest that all these laws indeed are score learning losses rather than only distribution learning losses? So for in this case, the implicit score matching were reduced to the form we're familiar with, which is the L2 norm plus its divergence, and the denoising loss will reduce to the term where you're matching the score function with a conditional score function. Right. But the denoising Markov model is amazing work and has a really good, brings very deep understanding of diffusion model. But one thing is that it's only focused on diffusion model of one modality. So we can actually easily extend that to make it multimodal. So let's say we have n different type of modality, and we just denote this big process bolded xt, which consists of this n different dynamics, which each of these dynamics is a potentially different Markov process with a generator Lxi. And so this itself serves as a forward noising process. It starts from the data distribution and turns to some prior distribution independently for each of them. Now to learn this model, we mimicking what we've seen for denoising Markov models. We need to learn some distribution in whole PT. Now it's the joint distribution of all these n different elements. And by slightly modifying the proof, we'll be able to deriving the loss we need to in order to learn this multimodal denoising Markov models. And now in each of the term, instead of just one L, we'll be summing all the generator of each component. And another difference is that now we have to take expectation over this joint distribution. So that's why we put it as bolded xt. Similar things happens here for implicit score matching and the denoising score, generalized implicit score matching or generalized denoising score matching as well. So with the correct objective derived here, we can return to the original example we're interested in, that is how to learn this continuous discrete diffusion model. So let's say we took this as our forward noising process. We can derive its time reversal which look like this. So although seemingly complicated, we know that there's two important facts. The first one is that the backward dynamics for X is still some sort of SE, and the backward dynamics for Y is still some sort of a continuous time Markov chain. Just the drift and the transition rate matrix are different, and they're in fact coupled because now the transition rate of Y depends also on X, and also the drift for X depends on Y. To learn this backward process, we can see from the form that now since we're working with more than one data modality, we need to learn the score of a joint distribution, which has two terms because we have two modality. For the Euclidean one, we'll have the usual.
I have a question.
Sure, yeah.
Yeah, sure. I noticed that although the continuous drift term relies on the discrete term, it's not like the vice versa. So it seems that the QT only relies on the continuous one XT, but not on the YT.
I see. Yeah, that's the thing is it also depends on YT itself, but essentially because YT, the transition rate matrix YT is a big matrix, so I just abbreviated the dependency of the transition rate of this QT here. It will actually pop up in this index. So let's say at YT, we really need to only evaluate is this QT YT at entry Y prime YT. So it's only part of the entries. But I abbreviated this for the notation. But in fact that they dependent on each other.
Well, thanks.
Yeah, thank you for the question. So as we're saying that now we need to learn the score of joint distribution, which has two components. We need the usual gradient log with respect to X for the joint distribution, as well as this probability ratio, which is the which at different position Y for the discrete score. If we look at this multimodal, if we took the learning loss from this multimodal DMM framework, we will see that the training objective, the denoising version of the training objective actually writes like here, where you are matching the X component. Let's say we parameterize this score with neural network S theta X, and parametering this one with neural network S theta Y. The X component will be matching with a conditional score, conditional X score of the joint conditional distribution, and Y1 with the Y component of the joint conditional distribution. But interestingly, if you apply Bayes' rule, will be easily simplify these two terms, saying that this joint conditional score is actually identical to the unimodal conditional score, where we're only adding noise to the X component. Similarly, the discrete score conditional score will be the same. The multimodal joint discrete score will be the same as the unimodal discrete conditional score. So if we plug in back, this actually simplifies to this expression, where we're seeing that we're actually matching the neural network with the unimodal conditional score and for both of the modality. So this has the important takeaway that training multimodal diffusion model in this framework is actually as simple as jointly optimizing a sum of unimodal diffusion losses. So this actually justify a lot of the heuristic approach done by practitioners, where they just add the modality and the losses for different modality, but it still will be able to work. The reason is that this loss actually trace back to the multimodal denoising Markov model loss we've seen before, and the score on truth will not be the unimodal scores for each of the modality, rather than the one for the joint distribution. So that's why we can the general modeling can work. So through this framework, we address this question of unconditional joint generation, because we can start now from a coupled prior distribution and turn to data distribution. But this haven't addressed the question of doing modality conditional generation, which is what a lot of people care. They also call this any-to-any multimodal generation. which refers to the capability that you want to, be able to condition on some modality of the some of the modality and then generate of the rest of it as a conditional distribution. We can in fact achieve this with a simple tweak of the design by introducing a decoupled time. So what we mean by decoupled time is that if we go back to the multimodal DMM, now instead of having the same time t for each of the dynamic, we can now allow it to have a different time for each of those. So let's say now we can have at most n different time t1 to tn. Each of them change freely from between 0 and t. So this means that now we want to learn, we have a new time variable, which is bolded t, consider a set of these t1 to tn. And now we'll be learning the distribution p bolded t is not only the joint distribution of all these n different components at the same time, except at any combination of the time. So, but I want to also mention that this idea of decoupled time, it's actually, of course, we didn't really invented it. It's this history of being used in enabling any-to-any generation can trace back at least to unit diffuser from 2023. And also it's adopted in multi-flow in 2024. I'm sure there's more work that discuss this. But what we do is that instead of treating this only as a trick, we want to justify that we want to include this design into the theory, saying that we actually can learn this property and it will give us what we want. So similarly, with the decoupled time, we can rewrite this objective. There's not much difference except for now there is more than one time input into your loss in your neural network, and in fact you're now taking expectation with respect to all these different time independently. Yeah. So by introducing this decoupled time back into this continuous discrete diffusion model, what we have, the only changes now is that instead of having only shared time t by both x and y, we now have two different time t and s. So this means that now we'll be learning score of the joint distribution at different time. And in fact, the loss has two different components, where the first one depends on the matching target is the conditional score at time t. The second part is the matching target is the conditional score at the time s. Learning this after introducing this decoupled time, there's one additional benefit which is crucial for any-to-any generation. Is in fact that this joint score at different time is equivalent to a lot of conditional score at different time. So just by applying Bayes' rule, we can see that the joint score with respect to x and time ts is in fact equivalent to the conditional score of xt equals to, at time t given ys. And similar things happens for the discrete score. So this big takeaway that learning joint score at different time learns a lot of corresponding conditional scores enables a very flexible sampling of the model, such as this any-to-any generation. So why is that? There's a crucial observation that if we learn this decoupled score with decoupled time, essentially we're learning distribution of this law and any possible combination for TNS. And then one way of using that is to simulate only part of the dynamics. Let's say we given partially noisy text ys, we only simulate x dynamics, and we'll be able to simulate actually be able to generate the conditional distribution of data x given ys. And similarly, if we're given a partially noisy image xt, we simulate only the y component. We'll be generating some data conditional distribution of the text given images. So in the special cases where we put actually thin ys and xt, we actually are performing image generation condition on text and text generation condition on image just through this simple dynamics with one model, right? But there's more way of using that. Since we're learning all sorts of combination of score. Instead of only traversing the usual curve, which is T and S, as is visualizing this curve 6. So from pure noise, we can pick, of course, we can pick T equals to S and go directly into the king data. But of course, since we learn all sorts of combination across this 2D time plane, we can also do curve 5 and 7, which means that one modality moves slower than the other. So this allows us to flexibly sample the model in a post-hoc fashion without worrying about it the first time in the design. In the extreme cases, we can also reduce this to two-step generation, where we follow in the edges of this two-time plane, where we first, for example, this means that we first unconditionally generate an images, then unconditionally on the image, we generate text caption. Or the other way, where we first generate text caption, and we do text-to-image generation in order to generate the text modality. There's a very flexible way of sampling the model. We indeed tried that to see that these different way of sampling give different results, but we haven't really figured out which one is the best for this framework, and we will leave that for as a future investigation. Apart from a flexible sampling, the decoupled design also gave a very interesting new guidance scheme. So if you look at the classify free guidance that everyone's using, essentially says that if we want to conditionally generate X given some condition, like say text king, text Y, you want to contrast your conditional score with the unconditional score, which essentially is equivalent to having no condition input in our setting. But there's work saying that okay, this is actually not the best way of doing guidance. A more ideal way would be to contrast your conditional score with a corrupted version of the conditional score. Typically, the corruption could be, say, having another model which is smaller or is undertrained. But in our model, and a very simple way of adding a corruption is just to add the corruption of the condition. So instead of inputting fully corrupted data, we can input the partially corrupted data. And this guidance actually works better. As you can see from the figure, where we evaluate FID of the image text generation on MS COCO, when sigma equals to 1 corresponds to classify free guidance, the optimal results actually falls in where sigma is ranging between 0.6 and 0.9. So that is the regime of this noisy guidance. So suggesting that this actually works better than the classical CFG. And there's also a more general way of using those. In fact, it can even enhance unconditional generation for as long as we are moving TNS both simultaneously. As long as we noise one of the part to be to a noise level larger than the current level. So with all these design, we can look at several applications like text image cogeneration. So here I'm showing some of the quantitative example. Each of them showing that the generated images are consistent with the text. But more quantitatively, we can look at the FID of this text image generation. I want to bring to your attention that across all these methods, we have a minimum use of encoder, and we do not rely on any pre-trained model, as we want to keep it as we wanted to see how good our algorithm is. And we have actually a very small model, but still achieve very decent performance of FID 16, using a very minimum training data and training compute. Another application is tabular data, as I promised before. And this one, our method achieves near SOTA performance using a significantly smaller model. So in all this past work like TabSync, we use VAE and a very large scale backbone with a parameter up to 11 million. Our network just requires a parameter of 64K while achieving very similar performance, if not better. So all this suggests that doing natively on the doing multimodal generation with diffusion model natively on state space might be a better one rather than compare with all these complicated pipelines that adopts VAE and tokenizers. Yeah, but that's all I want to talk about today. Thank you for listening, and this work cannot be done without all my amazing collaborators. Thank you for your attention.
Thank you. Is there any questions?
Hi. May I ask if the joint modeling the joint this diffusion, can this work on the ODE formulation of the continuous data with the discrete?
Yes. Yes, you can similarly derive the probability flow ODE for the continuous version. We have this formulation discussed in the appendix of the work.
So what about this kind of deterministic generation thing?
Yeah, so for deterministic generation, since we're actually coupled with if we're for now, I'm gonna say that if we're working with conditional generation, that's gonna be for sure, because essentially what you're simulating is the X part. If we're going to work with joint generation, because there lacks of deterministic sampler of the discrete diffusion, I would say that would be a bit more challenging. But recently, there's also some work who explore like a deterministic generation of discrete diffusion, but we haven't really considered that in our work. So I believe if you have some discrete diffusions capable of doing deterministic sampling, and then you will be able to do deterministic sampling of joint generation. Yeah.
But
Okay.
also,
Yeah.
in some sense, the CTMC is deterministic by itself, right? It's a deterministic process where you just evolve the probability masses.
Yeah, but I'm just wondering, so for example, if you do like continuous data deterministic generation, all the stochastic is coming from the prior. But if you do like this discrete generation, the stochastic is from the generation process, right? Not from the prior, because prior is fixed. So you do need to model the coupling of the a discrete generation process and the prior noise, right, to capture.
But the CTM, so if you are given a prior distribution, the CTMC just evolves the prior deterministically, right? And then all the stochasticity also comes from in some sense from the prior as well.
I see.
Yeah, that is a great question. Thank you.
If there's no questions, I have a question. Maybe I missed that part, but I remember you mentioned that at some point we don't want to do this alignment because some modalities just do not have so many data. But
Yes.
if I understand this correctly, you just sum the loss is like sum over all the modalities for this network. But if there's not enough data, how you train it?
So so there's two different things. So first of all, training VAE is a different task of essentially training VAE is about compression. It's about learning aligning the data model, aligning the latents. It potentially requires more data. Of course, it depends on the property of the distribution, but in many cases, it requires more data than training only a diffusion model. So, for example, let's say we work with generate images on CFAR. For sure, we can use the stable diffusion VAE, but that one is not trained on CFAR. The other one is trained on much larger text image corpus, but still the performance still has a lot of artifacts. So the scale of the data required here is different. So that's why we want to bypass that. Potentially with much less data, that is not enough to train a good VAE. You can still train a good generated models on the data.
Oh, I see. Thank you. Yeah, it makes sense. Another question related to this is like, how you ensure this modality align well with each other? Maybe I missed that part, or it's like if you just it's just from the data, or you have some mechanism, because if you have multiple VAE or something, you can I don't know, like you can align the latent or something. But here it just sounds like it's like training them together.
Yes. Yeah, I see the question. Yeah, the alignment of the data actually comes natively through the training, because while we are training, the data pair, the data distribution, each of them are coupled. So so essentially in the training, we're not assigning random coupling between in the modality of each data. So
I
the
see.
information passed through a neural network, and ideally, the neural network should be able to learn that the representation implicitly learn some representation that this modality will correspond to the other part, even without specifically enforcing that.
Yeah, I see. But I'm not an expert in this, but I was thinking if the pair in the data is noisy, will this become an issue if there's no explicit alignment mechanism?
I guess because our coupling only come from the data. If you have extremely noisy coupling, saying that the coupling is almost as random,
No,
then
I mean,
our method will, yeah.
I was mostly thinking like image and text is like a caption for that. It can have a lot of choice, like your cat, you can have like the caption you mentioned. It can also be like just a cat, right? Or
Yeah. Right. I guess then that depends on depends on like what's the type of a data set, also how long typically you trained it on. In our problem, in our application we train on MS Coco data sets, which tag captions are usually of the similar style, right? But of course, if you want to scale this to really big models, we'll have very diverse captions, and then I guess the model will be able to learn more complicated coupling between data sets, and even following, for example, instruction tuning, where it allows you to follow your instructions to generate type of captions. But now we haven't explored that. But that's a good things to do in the future. Yeah.
Yeah.
I see. Thank you.
Hi, I have a related question. So what about if you have like paired data, but I also give you some unpaired data? Can this unpaired data help the training of the joint modeling?
Yeah, I would say it can, because in fact it is actually kind of important, but not theoretical level, but from the practical level. So in this in the numerical experiment section, we found that this method actually could benefit from pre-training. So let's say although I have two different modalities, the method would benefit. Let's say if I only train on image generated model, I initialize it from the image part, I initialize text part from unconditional, something is trained unconditional on the text. The method still will benefit from that initialization. But then I can still use the pair data to keep training to align those. But the more data, it still helps the generation performance.
Yeah, so maybe I not mention the pre-training thing. So for example, like the traditional joint models, like for example, PCCA, like probabilistic canonic correlation analysis, right? They can do like, okay, I maximize the joint likelihood, plus if I have some unpaired data, I maximize the marginal single variable, right? So it's like a joint term. So yeah, so do you have this something like this?
No, it's not in the theory framework. It's just something we consider in practice. Like we initialize the model with something well pre-trained on the unpaired data, but then we calibrate that on the paired data. Yeah,
I see.
It could be something helpful in real practice. Yeah.
Yeah. Thanks for the talk. I have a quick question. So
Mhm.
basically for this joint modeling, you still maybe this is related to Jiajin's question. So you assume the independence between different modality, right? So you don't have this correlation in the like different modality. So that means in the sampling step, so actually given ST, when you predict the ST-1 is still independent between the modality.
No, I don't
That's
think so. I don't think
You mean
so.
adding noise, or you mean adding
No,
noise,
no.
or
I mean when you do the denoise.
when I do the denoise?
Yes.
The denoise is always coupled. So because you see actually we're learning the score. The score captures the joint distribution of the process. So naturally it depends on both X and Y. So there's no decoupling through the generate process.
No, actually what I mean is that more like the discrete diffusion model. So even though implicitly this could capture the joint distribution, when you do the
Mhm.
one-step denoising, like given the previous step, you denoise the next step, right? So, but
Mhm.
actually, the dependence between the mask token is actually independent, right? So because you somehow for the CTMC you still assume a independent around the different dimension. So here you also have this kind of assumption for different modality X and Y.
I'm not sure if I get your question, but you see that here, let's say we start with a pure mask token.
Yes.
To unmask each of the position, not only depends on your mask token, but also depends on at this time what's
Yes,
your
it
X
also
bar.
depends on your X. Yes, but
Yeah, it depends on our X.
let's say, so let's say for the discrete, you mask 4 tokens at the same time. So this 4 token is independent, right? So when you do this unmasking, would you predict the tokens? So you predict these 4 tokens independently.
Oh yeah, that's the
Yeah. So this
that's
is
the
actually
training. So in the training, we add independently noise to each modality, so that's fine. We can independently mask each token. But in the inference, we sequentially unmask this token, so that to make sure at each time only one step. If we want to avoid generation error, we unmask token one by one. So that in this case, even we're learning a mask, we're still, even if we're only learning this mask predictor, we can still learn the joint distribution. This is like the standard practice in discrete diffusion model training and inference.
okay. Yeah, thanks.
Sure if this. Okay, I hope this answers your question. Yeah, we can discuss offline. It's fine.
I think it really depends on how you discretize the backward process. So at the continuous level, these X and Y's are all coupled. And then if you discretize, there's no reason that X and Y are only changed like one by one. I think it's really dependent on how you implement it. But if you're only looking at the discrete component, if you're using forward process as a mask diffusion, and then yes, you're basically unmasking token by token, so it's a sequential like Yuchen mentioned. But there's no reason that the same thing applies to the correlation between X and Y.
Okay. Yeah, thanks.
Thank you.
Okay. I guess, is there any other questions? If there's no more questions, let's thank Yuchen again. Thank you very much for coming. It's very, very nice talk. Learn a lot from it. Yeah, thank you. So,
Thank you very much.
bye-bye, guys.